Hello everyone. Welcome to online class on ray optics and optical instrument. I am Barnali Bhattacharya, your physics teacher, and today I am going to discuss about a very important topics of optics, that is derivation of refraction formula at convex spherical surface. Okay. In my previous lecture, I have already discussed what is spherical refracting surface and types of spherical refracting surface, that is convex spherical surface and concave spherical surface. And I have also derived the refraction formula for convex spherical surface where the object lies in the rarer medium and the nature of the image is real. Let's start the class. So today I am going to discuss another case where the object lies in the rarer medium, but the image formed is virtual. So student, you can see the ray diagram here. Okay. So from this ray diagram, AP is the convex refracting surface. And this convex refracting surface separates the denser medium of mu2 and rarer medium of refractive index mu1. Okay, this refracting surface separates these two medium. Now, for this surface, what is P? P is the pole here. This is the radius of curvature, and this is the radius of curvature, and this line, that is the principal axis. And what is C? C is the center of curvature. Here, O is the point object. O is the point object, lies on the principal axis. Okay. Now, two rays of light from O incident on this refracting surface. The first ray is OA and second is OP. These two incident ray after refraction appears to diverge from a point on the principal axis, that is I. Appears to diverge from I. So what is I? I is the virtual image of O. Okay. See here. First ray, for the first ray, OA. OA incident at an angle I at A. Okay. After refraction, here light is traveling from rarer to denser medium. So after refraction, this ray bends towards the normal. Okay. If this ray after refraction bends towards the normal. And another ray OP is there, which goes undeviated as it incident normally, so it goes undeviated. These two rays appears to diverge from I. So I is the virtual image of O. Now for derivation. Let's draw a perpendicular AM on principal axis. Okay. What is I here? I is the angle of incidence and R is the angle of refraction. I and R are very small. And there are alpha, beta, gamma are the angle that's created by the incident ray, refracted ray, and normal with the principal axis. And they are also very small angle. Okay. Now, let's start the derivation. First of all, we will take a triangle, that is AOC. A triangle AOC. From this triangle, we can see what is I here. I is the exterior angle, and what is alpha and gamma? Two non-adjacent interior angle. And we know that the exterior angle can be represented as a sum of two non-adjacent interior angles. So from this triangle AOC, we can write I, that is the exterior angle, as a sum of two non-adjacent interior angle, that is alpha plus gamma. Is it clear? Okay. Now we can take another triangle. Another triangle, that is AIC. AIC. From this triangle, we can see that R is the exterior angle. Am I right? R is the exterior angle here. And what is beta and gamma? Beta and gamma are the non-adjacent interior angle. So R can be represented as a sum of beta and gamma. So we have now two equations. One is I and another one is R equal to alpha plus gamma and another R equal to beta plus gamma. Two equations are there. Okay. That is, our first aim is represent I and R in terms of alpha, beta, gamma. And we have already done this. Okay. Now we don't know the value of alpha, beta, and gamma. We want to calculate this. So for this, we can take one triangle, that is AOM. From this triangle, AP is perpendicular, OM is base, OA is hypotenuse. So from this triangle, that is AOM, we can write tan gamma equal to, tan alpha equal to perpendicular by base, that is AM by OM. I have already written. From triangle AOM, we can write tan alpha equal to AM by OM. Now second, I want to calculate the value of beta, and for this, I have taken AIM triangle, and from this triangle, we can write tan beta equal to AM by IM, that is perpendicular by base. Similarly, I have written tan gamma from ACM triangle, that is tan gamma equal to AM by MC. Okay. Now I have already told that alpha, beta, gamma are very small angle. Okay, because all the rays are paraxial and so alpha, beta, gamma and I are small. So for a small angle, we can write tan alpha equal to alpha, tan beta equal to beta, and tan gamma equal to gamma. See here that tan alpha can be written as alpha equal to M by OM. Tan beta can be written as beta equal to M by IM, and gamma can be written as tan gamma M by MC. Okay. Now we know that in our NCERT syllabus, for all convex, for all spherical mirror, spherical surface, and lens, that we have taken already. We have actually taken an assumption, that is they are small aperture. They have small aperture. Okay, as the aperture is small, if the aperture is small, then here what happened? M is very close to P. Aperture is small, so M is very close to P. So M can be replaced by P. So alpha can be written as Ap by OP, beta can be written as Ap by IP, and gamma can be written as Ap by PC. Okay. Now we have the value alpha, beta, and gamma. Okay. Again, the ray of light here traveling from rarer to denser medium. So we can apply Snell's law here. What is Snell's law? Snell's law, sin A by sin R equal to mu. That is refractive index, a constant quantity, that is refractive index, can be represented as a ratio of sine of the angle of incidence to sine of the angle of refraction. So we can apply here Snell's law, that is sin A by sin R equal to refractive index of medium 2 by refractive index of medium 1. Now cross multiply this. Mu to sin I, mu to sin R equal to mu1 sin I equal to mu to sin R. Now again, I and R are very small. I and R are very small, so sin I can be written as I and sin R can be written as R. So this equation become mu1 I equal to mu2 r. Now we have already represents I and r in terms of alpha, beta, gamma. That is, I is alpha plus beta. First equation you can see your first I can be written as alpha plus gamma, r can be written as beta plus gamma. Okay. So mu I have written I equal to alpha plus gamma and mu2 equal to beta plus gamma. Now alpha, beta, gamma, we have the value. Now put this. We have already put this, and we can now from this from both sides, left hand side and right hand side, AP can be taken as common, and we can cancel AP from both sides. Then we have mu1 1 by OP plus 1 by PC equal to mu2 1 by IP plus 1 by PC. Okay. Now what is OP? What is PC? What is IP? OP is nothing but the object distance. IP is nothing but the image distance, and PC is nothing but the radius of curvature. Okay, now see, in both sides, 1 by PC are there. So we can simplify this like, okay. After simplification, we get this equation like this. Okay. Now we will use the new Cartesian sign convention. Now sign convention, according to sign convention, what will be the sign of U and V? Both are on the left side. Okay. Both are on the left side of pole, that is opposite direction of, we are measuring this on the opposite direction of incident ray. So U and V will be negative. Only R will be positive. Object distance OP is negative, IP is negative, only radius of curvature PC is positive. Now let's put this value. After putting, we have mu1 by minus U minus mu2 by minus 3 equal to mu2 minus mu1 by R. Okay. Now minus minus plus, so mu2 by V minus mu1 by U equal to mu2 minus mu1 by R. This is the refraction formula, or required refraction formula. Okay. Now we have it. I hope there is no problem with this derivation. Now we'll discuss about the case 3. In this case, the object lies in the denser medium. In first two cases, we have discussed, that is, object lies in the rarer medium. Now we'll discuss the object lies in the denser medium and the image form is real. Okay. Let's see the ray diagram here. Okay. In this ray diagram, you can see KPL is the refracting surface, convex refracting surface. Okay. And here, the point object lies on the denser medium. Point object lies on the denser medium. And what is I here? I is the real image form. Okay. So here object lies on the denser medium and image on the rarer medium. And ray of light traveling from denser to rarer. So two incident ray are there. For first ray wave, incident at point A, and NC is the normal. So here ray of light traveling from denser to rarer. So after refraction, it bends away from the normal, denser to rarer. You can remember, away from the normal. And this refracted ray after refraction meet at I on the principal axis. So I is the real image of O. Let's start the derivation same way. We'll do the derivation the same way. See here, we'll take first we'll take a triangle, triangle AOC. From AOC, what is the exterior angle? In this case, gamma is the exterior angle, and that can be represented as a sum of two non-adjacent interior angle, that is I plus alpha. Okay, and from this we can write I equal to gamma minus alpha. And from triangle AIC, what is the exterior angle here? R. R is the exterior angle. R can be written as gamma plus beta. So we have now the value of I and R, the angle of incidence, and R in terms of alpha, beta, gamma. Now we'll follow the same step. Same step we'll follow here. From AOM, from triangle AOM, we'll calculate the value of tan alpha, that is perpendicular by base, AM by OM. And from AIM, we'll calculate the value of beta, tan beta. And from triangle ACM, tan gamma equal to M by MC. Okay. Now we know already that alpha, beta, gamma are very small angle because all the rays are paraxial. So alpha, beta, gamma all are small angles. So for small angle, you can write tan alpha equal to alpha, tan beta equal to beta, and tan gamma equal to gamma. Okay. We have already done this. Now again we use the assumption, that is aperture for this refracting surface, aperture is very small. For small aperture, we can take P and M very close. So we can replace M by P. Okay. We have already done this. As the aperture of the spherical refracting surface of small, then MP is very close to M. Then alpha can be written as AM by OP, beta can be written as AP by IP, and gamma can be written as AP by PC. Okay. Now we will use Snell's law. Same step. Okay, same steps are there. We will use here Snell's law. What is Snell's law? Light is traveling from denser to rarer. So angle of incidence is I, angle of refraction is R. So sin A by sin R equal to what? Mu1 by mu2. Okay. Mu1 by mu2. So now cross multiply this. That is mu2 sin I can be written as mu2 sin by sin I equal to mu1 sin R. Now I and R are very small. Again, use the assumption sin I can be written as I and sin R can be written as R. Okay. And put the values of I and R. I equal to gamma minus alpha and R equal to beta plus gamma from equation 1 and 2. Okay. Now alpha, beta, gamma, put the value of alpha, beta, gamma from there. Now some mathematical steps are there, very easy mathematical steps. We can take AP common from both sides and cancel. After that, mu2 equal to 1 by PC minus 1 by OP, mu1 equal to 1 by IP plus 1 by PC. Okay. Then we can simplify this like this. We can take both PC term on the right hand side. And after simplification, we have like this. Okay. Now what is IP, OP, PC? What is OP here? OP is the object distance. What is PI? PI is the image distance. What is PC? PC is the radius of curvature. Okay. Now we will use the sign convention. According to sign convention, what is OP? OP is minus because left side. Okay. It is we are measuring this from the pole and opposite direction of incident ray. That's why it is negative. So R is also PC, that is R, radius of curvature, that is also negative. U is negative, R is negative, only the image distance PI, that is P, is positive. So put the value and simplify this. And after simplification, we get the refraction formula. Okay. I hope there is no problem with this derivation. Now second. Now last one, that is case 4. The object lies in the denser medium and the image formed is factual. You will follow the same step, same method, everything is same. Here I am just giving you the ray diagram. From this ray diagram, do this in exactly the same way. It is your homework. Okay, it is your homework. You can do this. Okay, student. Then in this lecture, we have already derived all the refraction formula for convex spherical surface. In our next class, we will derive this formula for concave spherical surface. So bye, student.